So welcome students. In last week we have studied about the momentum balance. So we have derived the equation of motion and equation of equation of motion and Navier-Stokes equation. So in this week we will study about the macroscopic balance as well as the we will solve the third axiom of the transport phenomena, which is the energy is conserved. So first axiom is the mass is conserved, second axiom is the momentum is conserved, and third axiom is the energy is conserved. So in fluid mechanics generally we use the first and second axiom mostly, and but we also use for some extent the third axiom, that is the energy is conserved. This axiom is generally used to calculate the amount of energy required or the requirement of energy to flow the fluid from one point to other point. So we will start with the macroscopic balance. So basically in last weeks we have studied about the equation of continuity. We have solved the problem related to the equation of continuity and equation of motion at the microscopic scale. So what is the microscopic scale? In microscopic scale we take a control volume, then we make a in a system. The control volume is a part of a system. For that we have written the mass balance, then momentum balance, then we assume we will allow the control volume of the control volume tends to 0. When the volume of control volume tends to 0, then the equation will become the differential equations. Now you can use you can use the differential equation to solve the problems, to calculate the velocity at a given point, or to calculate the shear stress at a given point. There is another approach to write the mass balance or momentum balance, that is called the macroscopic balance. In macroscopic balance we write the balance for whole system. Instead of writing the balance for a control volume, then allow the volume to tends to 0, we write directly the material balance or mass balance for whole system. So based on the requirement, if you want to directly calculate the average velocity of a system, or what is happening overall the system, then you can use the macroscopic balance. So I am just giving you the example of macroscopic balance. But first thing, why we require the macroscopic balance at this point? Because when we solve the problem related to the energy balance, in energy balance generally we want to calculate the requirement of energy for whole system. We don't want to calculate at given point what is the energy requirement. We want to calculate from for a given pump or for a given system what is the energy requirement. So macroscopic balances are more useful when you want to calculate the energy. But when you want to calculate a velocity at a specific point, then you have to go for the microscopic balance. So I am just giving you an example how to solve the macroscopic balance. So in equation of continuity, when you derive equation of continuity in the microscopic balance, you will end up the equation for the incompressible fluid, you will end up the equation dV del dot V equal to 0. But when you write the macroscopic balance, suppose you have a system. Macroscopic balances are the system based. Suppose this you have a system. Here you have the velocity v1. This is a pipe which has the cross-sectional area, circular pipe which has the cross-sectional area of a1. Here you have the velocity v1. Density of the fluid is rho1. This is a process. After process, you have this is the entering point, this is the exit point. You have a circular pipe of velocity of cross-sectional area a2. The velocity of fluid is v2 and density is rho2. So you can just write the equation that input equal to output plus accumulation, or input minus output equal to accumulation. Accumulation means how much mass is accumulated in the process. So this is the overall material balance for the system. Here we are not taking any control volume for solving the problem. Here we are making the material balance for overall system. So at a steady state, accumulation will 0. There is no accumulation in the system at a steady state. Same as we have done for the microscopic balance. So for at steady state, you will end up rate of input equal to rate of output. So of mass. So if rho is density, then you can write dense mass flow rate m equal to rho 1 v1 a1. Rho is the mass per rho is the density, that is kg per meter cube. V is velocity, that is meter per second. A is cross sectional area, that is meter square per second. So mass flow rate, the mass and the rate of mass entering in the system is rho 1 v1 a1. Similarly, the rate of mass leaving from the system is rho 2 v2 a2. So you can just write equation of continuity in this case m is mass flow rate, the unit of m is kg per second, m equal to rho 1 v1 a1 equal to rho 2 v2 a2. So this is the macroscopic balance equation, which comes when you do the when you do the balance overall system. You are not doing the balance for a given point, you are making the a balance for system. Now suppose you have a problem, we will just take a problem, flow of crude oil and mass balance. Here petroleum crude having the density 892 kg per meter square is flowing through a pipe arrangement shown in the diagram. So this is the diagram. Here fluid is entering from point in the pipe 1, then it flows to pipe 2, then it will distributed in pipe 3. So this is the 2-inch pipe, this is the 3-inch pipe, this is the 1.5-inch pipe. Okay. Now at a total rate of 1.388 multiplied 10 to the power minus 3 meter cube per second. So this is the volumetric flow rate of fluid entering in the pipe. Now flow divides equally in the 3 pipes. Pipe 3. So here flow is dividing in this pipe equally. The amount of fluid flowing in this pipe and fluid flowing in this pipe are equal. So the steel pipe are schedule 40 pipe. Calculate the flowing using SI unit. First, total mass, flow rate m in pipe 1 and pipe 3, average velocity v at pipe 1 and pipe 3, mass velocity g in pipe 1. So basically you have to calculate you have to do the material balance, or you have to write the equation of continuity, macroscopic mass balance for the system. So here one thing I have to explain you that here it is given that the steel pipe are schedule 40 pipe. So what is the schedule? Basically what's happened in market, because you have to whenever you see a pipeline, there are several joints in the pipeline, there are several type of fittings which is used in the hydraulics. So when you want to make a pipeline or design a hydraulic system, then it is important that you have the commercially available pipelines, and the fitting should have the standard size. So what are the important parameters for a given pipeline? There is a diameter of the pipe. When you define a diameter of pipe, it might be a internal dia of pipe, it might be a outer dia of pipe, or it might be a nominal dia, that is the average of the internal and outer dia. So generally pipe is defined by a nominal dia. And then thickness of the pipe. So if you want to use a pipe for higher pressure, you need a thick pipe. If you want to use a pipe for the lower pressure, then you need a thin pipe. The thickness might not be much high for the lower pressure pipe. So there are some standards which is available in the market, that is called the schedule numbers. So schedule numbers define the size of the pipe. What is the nominal diameter of the pipe? So here it is given that the steel pipe are schedule 40 and nominal diameters are given in the here. So in the schedule numbers, you have to define the nominal diameter of the pipe. So this is the 2-inch pipe. This is the nominal diameter. This is not the outer diameter. This is not the inner diameter of pipe. This is the nominal. That is the average of outer and inner diameter. then you have to write the schedule number. So schedule number define the thickness of the pipe. So when you see the schedule number charts, then you can calculate the internal cross sectional area directly. So here already the cross sectional area are given. So in the exam, if this problem will ask to you, you will get the final cross sectional area of pipes. So here for 2-inch pipe, the cross sectional area are 2.165 multiplied by 10 to the power minus 3 meter square. For 1.5-inch pipe, the cross sectional area, this is the ID, internal diameter, and the cross sectional area is 1.313 multiplied by 10 to the power minus 3 meter square. So either you have given, either the internal diameter is given or the cross sectional area is given. If the internal diameter is given, you can calculate the cross sectional area by pi r square or pi d square by 4, है ना, pi radius square or pi multiplied by diameter square divided by 4. So in this way you can calculate the cross sectional area of the flowing channel. So once you know the cross sectional area A, this is the A, then here density is given. This is the density 892 kg per meter square. So this is the rho, because we assume that here there is a no temperature change and crude is a incompressible fluid, so density will not change. So this will be the same in all three pipes. Now rho is given, A is given, and this is the volumetric flow rate V. So when you divide V by A, so this is the cross sectional area, initial cross sectional area. When either you multiply by Q to density, you will get the mass flow rate. So here what they have done, they multiply by volumetric flow rate to the density and they directly get the mass flow rate. Or the other way you can solve, you can use the equation, multiply, you can divide the cross volumetric flow rate divide by cross sectional area, you will get the linear velocity. Once you get the linear velocity, you can calculate, use the equation, this equation, rho 1 A1 V1. Rho is density, A is cross sectional area, V which you calculated by Q by A. So that will become rho 1 Q1. So M1 equal to rho 2 A2 V2 multiplied by 2. Why 2? Because fluid is flowing equally in the both pipes. It is given here. So M3 equal to M1 by 2. So mass flow rate of the pipe 3 is 0.319 kg per second. This is the mass flow rate in the pipe. Then you can calculate V1. V1 equal to M1 divided by rho 1 A1. So V1 equal to 0.641 meter per second, and V3, that is M3 by rho 3 A3. So V3 equal to 0.528 meter per second. So this is the example of macroscopic material balance. So generally macroscopic material balance is used when you want to calculate the input and output flow rate for overall system. Instead of getting the, here the velocities are the average velocity. This is not a local velocity. When you doing the microscopic balance, you can calculate the velocity when you are using the equation of motion or Navier-Stokes equation. You can calculate the velocity at a local point, but here you are calculating the velocity, here you are calculating the average velocity, means velocity, average velocity at this point, average velocity at this point, and average velocity at this point. So this is the average velocity. Now we will move to the energy balance. So generally when we solve the energy balance, we will solve the problem by using the macroscopic balance. So this chapter I am teaching you from the Jing-Koblish book, Unit Operations, Transport Phenomena and Unit Operation, from Jing-Koblish. This is the chapter 2 from the book. Now this is the part which I have already covered about the macroscopic balance. You need not to go through here. Okay, one thing I am clearing you in here, that in this book Jing-Koblish, Transport Phenomena and Unit Operation by Jing-Koblish, here they have derived the equation of motion and Navier-Stokes equation using the microscopic balance on a in regular shape control volume which is flowing with the fluid. So this is the another approach to write the microscopic balance. What we have done in the microscopic balance, we are taking the control volume, size of control volume as a cubical size, that is the cube. So the shape of the control volume is fixed and the size is fixed. The next thing is the control, we have assumed that control volume is fixed in space. So control volume is not moving, only the fluid is moving. And then we have done the material balance and momentum balance. In this book they have derived the same equation by using the different mathematical approach. So here they use the basically the irregular shape control volume. Then they assume that control volume is in moving with the with the fluid. So here control volume is not constant, it is moving with velocity v. So this is the another approach. When you use this approach, you will end up with the integration, surface integration and the volume integration. So in the coordinate geometry. So this is mathematically, this approach is more rigorous or more complicated, but the number of steps required is low. So here you less. So here the number of steps required to determine the equation is only the 3. But in our case we have to use a lot of steps to solve the same problem. Okay, so this is the same answer with the different mathematical approach. Now we will move to the third axiom, that is the energy is conserved. So basically what is the third axiom? Third axiom tell that the energy is conserved. That means energy cannot be created and cannot be destroyed. So basically it is a first law of thermodynamics, which we have already studied in the thermodynamics. So chemical engineering thermodynamics subject. So here for the closed system we can write that overall internal change in internal energy equal to the heat thermal heat added to the system or heat removed to the system plus work done on the system or work done by the system. So this is the first law of thermodynamic or energy balance for the closed system. So you can see that here we are not using the differential control volume. This is the macroscopic balance. This balance is done on a whole system. This balance is not done on a part of the system. Control volume is a part of the system, which is a differential part of the system. This is not a differential part of the system. This energy balance is done on a whole system. We are assuming that system is closed, so nothing is entered, mass cannot be entered in the system. Then you can get this answer. So this is the macroscopic balances, energy balance on a closed system. So we can write the overall energy balance equation, that is the rate of entering the entity output minus rate of entity input plus rate of entity accumulation in a system is 0. Here entity is energy. So there are 3 types of energy which we can define. The first 2 types of energy are basically the mechanical energies, that is the potential energy and kinetic energy. Then third type of energy is internal energy. So the internal energy means the energy of the material present in the system, and potential and kinetic energy a type of mechanical energy, which is the energy due to the this is the energy due to the potential part, and this is the energy due to the movement of the process or of the system. So here you can write the total energy per unit mass is E. This is the total energy. Total energy can be written as the U plus V square by 2 plus Zg. U is the internal energy, V square by 2 is the, this equation is for per unit mass. V square by 2 is the basically kinetic energy, and Zg is the potential energy per unit mass of the system. Here this is in the English units where this is divided. Now This is the total energy. Now there might be, if you are assuming the open system, so in open system what's happened, the material can enter in the system and material can are removed from the system. So there might be work done by the material which is entering in the system, and there might be work done by the material which is leaving from the system, or system may done the work on the material which is entering on the in the system, or system may done the work on the material which is leaving from the system. So the work done per unit volume can be written as PV, pressure multiplied by specific volume. Specific volume is volume divided by per unit mass, volume per unit mass. So PV is the work done by the material which is which is entering in the system, or work done on the material which is entering on the system, or work done by the material which is leaving from the system, or work done on the material which is leaving on the system. So this is a part of energy. Work is also a part of energy. So here, instead of writing, when you add internal energy to the work done by the material itself which is entering in the energy in the system, or which is leaving from the system, then you can replace U plus PV to the H. H is the enthalpy. So U plus PV is defined by definition, enthalpy is U plus PV. So for the open system, here U can be replaced by H. Internal energy can be replaced by enthalpy. So the for open system, the overall energy balance is H plus V square by 2 plus Zg. This is the material entering in the system, then that is the material leaving from the system. You need not to go for this derivation, equation 2.76, equation 2.777, because here they are using the writing the equation by surface and volume integrals. So I am not want to confuse you that how this is come, because this is the another approach to solve the problem. This is basically a microscopic balance only. But when you write the equation for the steady state, which is more important for us in this point, so when you write the equation for steady state, at last you will get this equation, H2 minus H1 plus 1 by 2 alpha V2 square average minus V1 square average plus G Z2 minus Z1 equal to Q minus WS. So this is the energy balance, overall energy balance for a open system. Here alpha is a coefficient. I will discuss about the alpha. Alpha is a coefficient, and this is the overall energy balance for a system which has the 2 points. One is the point of entry and 2 is the point of leaving or exit point. So this is the entry point, this is the exit point. Q is the energy, thermal energy given to the system. W is the work done on the system or work done by the system. So this is not the work done by the material, this is the work done by the surroundings on the system. When you are talking about here, when you add H plus PV here, so this is the work done by the material itself which is entering in the system. But here this is WS is the work done by the surroundings, not the work done by the material. So this is a different work. So you have to just remember equation 2.710. This is the overall energy balance, that is equal to H2 minus H1 plus 1 by 2 alpha V2 square average minus V1 square average plus GZ2 minus GZ1 equal to, this is V2 average square, this is not V2 square average, this is the V2 average square minus V1 average square plus GZ2 minus Z1 equal to Q minus WS, where 1 is the entering point in the system and 2 is the exit point of the system. Now suppose this is the problem. Here fluid is entering from here, WS is the work done. This is the hydraulic system, a open hydraulic system. Here this is the point 1, this is the point 2. So fluid is entering from the point 1, V1 is the velocity of fluid, ρ1 is the density of fluid, P1 is the pressure of fluid. Fluid is leaving from here, V2 is the velocity, again the velocity is fluid, P2 ρ2 is the density of fluid, P2 is the pressure of fluid. In between you have a pump. So pump, what is the pump? Pump work is the pump is changing the converting the electrical energy to the mechanical energy, and that mechanical energy will act as a work on the system. So here you are working on a system, or if you are using the turbine, then the work done by the system on the turbine. So it might be a pump. If it might be a pump, then the work done on the system, and it might be a turbine. If it is a turbine, then it is the work done by the system. Then in between you have a heater. So you are heating the fluid. That means you are giving the thermal energy as a Q, as a heat. Q is a heat to the system. So this is the example of the type of system for which we can write equation 2.710 for overall material balance or overall energy balance. So this is the different units of the energy, BTU and to joule and horsepower 2 kilowatts. This is the units of energy. You might already know it. Now we will discuss about the kinetic energy velocity correction factor, which is coming here. First I will tell you why this factor will come. Basically what's happened here, we are writing the energy balance for overall system here to here, but as we have already know that the velocity at a local point are different. So in this cross sectional area, the velocity as at the surface of the pipe will be 0, velocity at the center will be maximum, and you have a velocity profile. So the kinetic energy at the pipe, at the wall of the pipe will be 0, and kinetic energy at the center will be highest. So you have a average kinetic. When you are writing the material energy balance, you are calculating the average kinetic energy. You are not calculating the a precise value of the kinetic energy. And when you are calculating the average kinetic energy, and here you are doing the V square of the average, then you have to, as velocity is changing, then velocity is changing. When you are averaging a velocity, then you are doing the square of the average. Then there should be a correction factor, otherwise the average kinetic energy will be different to the precise kinetic energy. So we are dividing this this component kinetic energy to a factor alpha. So it will come because we are writing the equation for a average velocity, not for a precise velocity. So I am not going to the derivation of this one again. Basically in this derivation they are calculating the what should be the correction factor when you do the averaging out, the velocity. So this is alpha will come, alpha equal to V average, means average velocity cube divided by velocity, local velocities at a the average of the cube of local velocity at different points. So this is equal to alpha, and alpha is for laminar flow. Generally you need not to define all the terms, you not to remember all the terms, you have to just remember this line here in page 60, that for alpha is 0.5. Here for laminar flow, the value of alpha in the kinetic energy term is 0.5. so this is the important result, that in the laminar flow you have, if the flow is laminar, you have to take alpha as a 0.5, and if the flow is turbulent, for maximum turbulent flow, the value of alpha is 0.945 to the around the 0.945, or it varies from 0.90 to 0.99, and generally for the turbulent flow, values alpha is taken as 1. So whenever you solve this problem, first you have to calculate the, first you have to determine that it is a laminar flow or it is a turbulent flow. So how you determine that it is a laminar flow, turbulent flow? By calculating the Reynolds number. So first calculate the Reynolds number in a circular pipe. If Reynolds number is less than 2100, that means it is a laminar flow, and if it is a laminar flow, take the value of alpha 0.50. If it is greater than 2100, that means it might be a transition flow or turbulent flow, and if it might be a transition flow or turbulent flow, take value of alpha as 1. Okay, so there is a thumb rule. You need not to go for this derivation. This is for your understanding only, but there is a thumb rule that alpha equal to 0.5 if flow is laminar, and alpha equal to 1 if flow is turbulent. Now this is some application of this example of the overall energy balance. This is not actually related to your subject, but if you want, you can solve this also. This is very interesting problem, and this is not very complicated problem, just problems related to the solutions. So if you want to interested in competition exam related to the chemical engineering, you should solve all these problems. Now the important part of here is the overall mechanical energy balance. So what's happened, the first law of thermodynamics or the third axiom of transport phenomena states that overall the energy is conserved. That means for a given system, overall energy is conserved. Okay, but if the velocity, the kinetic energy is not very high, or the velocity of fluid is not very high, so in that condition what's happened, or if you are not in this condition, what's happened, that generally the mechanical energy will not convert in the thermal energy. And when the mechanical energy will convert in the thermal energy, when you have a lot of losses, means your flow is very high, that means your friction is very high, or your fluid is very highly viscous. At that conditions, the mechanical energy will convert in the thermal energy. Means when the fluid is flowing, then you will see that fluid start to heat up due to the mechanical energy is converting the kinetic or potential energy to the thermal energy. Or either you are increasing the temperature of the system in this way that that density of the system is changing. If the density of the system will change, then the thermal energy will convert in the mechanical energy. So if you are not converting the thermal energy and mechanical energy in each other, or the electrical energy or nuclear energy in the mechanical energy, then you can also say, if you are not converting the other forms of energy in the mechanical energy, or if you are not converting the mechanical energy to the other forms of energy, then you can also say that the mechanical energy of a given system is conserved. So in fluid mechanics, generally we are solving the problem of fluid flow in a pipe. So this is the simple flow, and the velocities are generally not much higher, and generally fluid is liquid, water or air or any gas or any oil like crude oil or petrol, diesel in the most of the industrial problem. So in that problems, whenever you are solving this type of problem, generally you are not converting the thermal energy to the mechanical energy or other forms of the energy in the mechanical energy, and also you are not converting the mechanical energy to the other forms of energy in large extent. A small amount might be converting, but in large extent they are not converting. In this case, you can you can say that mechanical energy is conserved. So when you are saying that mechanical energy is conserved, you can write the new equation. So I am not going to the derivation. This is the final equation. So this is the final equation when you are saying that mechanical energy is conserved. One more thing, in this equation we are not assuming that the thermal energy may not convert in the mechanical energy. Here the mechanical energy may convert in the thermal energy, and thermal energy may convert in the mechanical energy. by using the Ws and F. So here this is the kinetic energy term, same term, this is the potential energy term, this is the pressure term which comes from the internal energy terms. Okay, this is the pressure energy due to the pressure. This is the sigma F is the losses, friction losses of the due to the this is the losses due to the friction or losses due to the change in flow. So this is the overall losses. Sigma F is the overall losses of mechanical energy due to the converting of the mechanical energy in the other form, and Ws is the work done on the system, so the by the surroundings. So it might be a pump, or if the work done by the system on the surrounding, that it might be a turbine. So this is the removing of the mechanical energy from the system due to the work, and this is the friction losses. So here we are not assuming that we are using a major component or major equipment to change the mechanical energy to the thermal energy, but there might be some amount of mechanical energy may convert in the thermal energy due to the friction losses. So that will consider in this equation. Okay, so this is the equation which we will use to calculate the energy requirement of a hydraulic system. Now if we are assuming that friction losses are zero, that I am already tell you that the when you are considering that the mechanical energy there is not converting in the thermal energy at all, so at that point you can consider delta F equal to 0, and when you are not adding any mechanical energy by surrounding, that means you are not using any pump, you are not using any turbine to convert the mechanical energy or the to convert the to add the mechanical energy in the system or to remove the mechanical energy from the system, then you can assume that Ws also 0. If friction is 0, then the sigma F equal to 0, then you will end up this equation, and this is the Bernoulli equation. So Bernoulli equation comes when you assume that work done on the system or work done by the system is 0, as well as the friction losses are 0, and when you incorporate the friction losses and work done, then you will get the overall mechanical energy balance equation, which is this equation. So this is the one equation 2.727. So in this equation 1 by 2 alpha V2 average square minus V1 average square plus G Z2 minus Z1 plus P1 to P2 dP by rho plus sigma F plus Ws equal to 0. So this is the equation which is used to calculate the to do the mechanical energy balance on a given hydraulic system, and this equation is used to calculate the power requirement or energy requirement of a given hydraulic system. So there are some numericals here, so you should read these numericals. So basically mechanical energy balance for pumping system, a water of density this 998 kg per meter cube is flowing at a steady mass flow rate through a uniform diameter pipe. The enter pressure of the is 68.9 kilonewton per meter square absolute in the pipe, which contain the which connects to a pump which eventually supplies the this much energy of the flowing fluid in the pipe. So here the energy is given, how much energy is given to the pipe. The exit pipe from the pump is the same diameter as the inlet diameter, so the pipe diameter is same. The exit section of the pipe is 3.05 meter higher than the entrance, so there is a difference between the height of the inlet and outlet pipes. The pressure of exit section is 137.8 kilonewton per meter square. So here the pressure is 68.9 kilonewton per meter square. Exit pressure is 137.8 kilonewton per meter square. ABS means absolute pressure. The Reynolds number of pipe is above 4000. So here you can assume that turbulent flow. Here the Reynolds number is already given, so you can assume the turbulent flow. Now they are asking to calculate the friction losses, delta F. Okay, so here all the things are given. So this is the diagram of the system which is given. Here fluid is entering, where a incompressible fluid, so density is not changing. So here the V1 is given, V1 is the velocity, P1 is the pressure which is given. Here P2 is the pressure which is given, V2 is the velocity, the height difference is 3.05 meter there, which is used to calculate the kinetic energy. The power supplied by the pump to the system, pump is a surrounding which supply the power to the system, it is given. Then you have to calculate the friction losses. So first, because from the first we will use the equation of continuity. So equation of continuity is rho 1 v1 a1 equal to rho 2 v2 a2. So here the diameter of pipes are same here and here, that means a1 and rho 1 are same. Okay, if diameter of pipe is same, then a1 and rho 1 a1 and a2 are same. Here the cross sectional area from entering point and cross sectional area at the leaving point is same, so diameter is same. Then another point is a1 rho 1 v1, rho is the density. So density, because we are taking a incompressible fluid, here it is given that a water with density this much, the water is a incompressible fluid, the density of water will not change with pressure generally so much. So here you are not heating the system, so density will change with temperature only. For incompressible fluid, density will not change with pressure, so the density will be same. So rho 1 equal to rho 2, so rho 1 a1 v1 equal to rho 2 v2, rho 1 a1 v1 equal to rho 2 a2 v2. So rho 1 equal to rho 2, a1 equal to a2. Now that tells you that v1 equal to v2. So velocity, whatever velocity you have here will be the same velocity you have at the exit point. So the velocity of fluid at entering point and exit point will be the same. Now if velocity of entering point and exit point will be the same, then the kinetic energy requirement will be 1 by 2 v2 average square minus v1 average square divided by alpha. Alpha is 1 here, so this v2 equal to v1, so kinetic energy requirement equal to 0. Then the potential energy requirement, that is Z2g. So Z2 is given, Z1 minus Z2 is given 3.05 meter, multiplied by G is 9.806. So you will get 29.9 joules per kg. This is the amount of energy required change due to the change in height. Now the pressure energy is given as P1 by rho. So P1 value is given and P2 value is given, and this is the rho is density. So you can calculate the requirement of pressure energy. So what is the unit of pressure is here? Pressure and density. Density is kg per meter square and pressure is given in kilonewton per meter square. So for you have to convert kilonewton per meter square to newton per meter square. That's why here you multiply it to the 1000. Okay, to converting the pressure in the newton per meter square. So you have the 69.0 joules per kg and 138.0 joules per kg. This is the exit pressure energy. This is the pressure energy at the entering point. Now from that equation you can write delta F equal to minus Ws plus 1 by 2 alpha V1 square minus V2 square plus G Z1 minus Z2 plus P1 minus P2 rho. So when you substitute all the value, here Ws is given in original problem. Ws is minus 155.4 joules per kg. So you have to just, okay, here when you are when we solving the equation here we are using the plus sign. That means here you assume that work done on the system is negative and work done by the system is positive. But if you are using the negative sign, then you can assume that work done on the system is positive and work done by the system is negative. So here, because this is the work done on the system, pump is doing the work on the fluid, so it will come negative. So when it will come negative, you can use the negative sign here, and you have to solve this equation. This is 0, this is minus 29.9, this is the 69, P1 by rho is 69.0, P2 by rho is 138.0. You will get friction losses as 56.5 joules per kg. Now we will see the next problem, that is the pump horsepower in fluid flow system. So basically this is in the English units, so you have to solve this problem in the English unit. So a pump draws 69.1 gallon per minute of a liquid solution having the density of 114.8 lb per pounds per feet cube from a open storage tank of a large cross-sectional area of 3.068 internal diameter of section line. The pump discharges its flow through a 2.067 ID pipe to a open overhead tank. The end of the discharge line is 50 feet above the level of the liquid in the feed tank. Friction losses in the piping system is this much. Here the friction loss is given, and you have to calculate the energy requirement of pump, or the which size of pump, because you are in the market. If you know that how, when you are going to the purchase a pump, it will come like 1 horsepower pump, half horsepower pump, 1/2 horsepower pump, or 1/4 horsepower pump. So here you have to calculate the size of the pump, which size of the pump required to flow the water from a tank to a overhead tank. The efficiency of pump is given, so you have to divide the whatever the power is calculated, you have to divide that to the 0.65, so you will get the actual power. So WP is the actual power of the pump, that is the WS, which is the mechanical energy requirement, divided by the 0.65, that is the efficiency of the pump, that will be the actual power of the pump. So this is the diagram of the system. Here it is given that you have a tank, overhead tank, where the fluid is flowing, where you have to transfer the fluid from this point to this point. Okay, and the difference between this point 1 and point 2 is 50 feet, and here the diameters are given. This is the 3.068 inch pipe, this is the 2.067 inch pipe. So you have to do the energy balance, and for this system, so energy balance will will happen from this point to this point. Okay, and then you have to calculate the what is the requirement of power of this system. Now first we calculate the flow rate of the system. Cross-sectional area is given, fluid, then you can calculate this is the volumetric flow rate is given. Okay, then this is the gallon per meter cube, so this is the volumetric flow rate in the gallons. So first we convert in the feet cube per second. So this is the volumetric flow rate in the British unit, in the feet cube per second. Then you convert, then we can calculate the V2. V2 is the velocity at the point 2. So this is the point 2 is the exit point. So we just calculate the velocity at exit point, that is equal to cross-sectional area volumetric flow rate divided by the cross-sectional area. Cross-sectional area is 0.0233 feet cube, because internal diameter is given here. When internal diameter is given, you can calculate the cross-sectional area. Internal diameter is 2.067 inch. So once you know the internal diameter, you have to just calculate using the pi r square the cross-sectional area. Now flow is turbulent. We assume that means alpha is 1, v1 is 0. Why v1 is 0? Now you have to understand this problem little bit more. Here we assume that v1 is 0 here. Why v1 is 0? Because here the cross sectional area is very large. So when fluid flows from here to here, the change in cross sectional area is very low. So the velocity of fluid at this point is 0. So then P1 minus P2 equal to 0 also. V1 is 0, that means V1 square divided by 2GC equal to 0. Then P1 minus P2 equal to 0. Why? Because in this diagram, this is the open atmosphere environment. So here the pressure is the atmospheric pressure. At point 2 also fluid is coming out from the system in a open atmosphere. That means pressure should be 1 atmosphere at this point also. So P1 minus P2 should be 0. Now you have to calculate V2 by 2GC. GC is a coefficient which is used when you solve the problem in British unit, and the value of GC is 32.174. Okay, so you have to remember this. When you solve the problem in the British unit, you have to use the GC, and the value of G is 32.174. So G and GC are same, and when you solve the problem in this unit, you have to use the GC also, British unit. So V2 is square by 2GC. So GC is 32.174, V2 is 6.61. V2 value we have calculated here 6.61. Just substitute this, you will calculate the energy requirement, energy due to the kinetic energy at point 2, that is the 0.678 fit LBF by LBM. Okay, now you have to calculate the potential energy change. So what is the potential energy change? That is the Z1. Z1 is 0. If you assume Z1 is 0 here, this is the initial point. Then the second point is 50 feet higher than the first point. So you just substitute Z2 is 50 in this equation and calculate the energy requirement. That will comes the 50 FTF FT LBF by LBM. So this is the unit for energy in the British British unit system. So this is the 50.0. So you just write, now you have to write just the equation, basically mechanical balance equation. So WS equal to Z1 G by GC minus Z2 G by GC plus V1 square by 2GC minus V2 square by 2GC plus P1 minus P2 by rho minus sigma F. So this is the mechanical balance equation in the British unit. There is a little difference, slight difference between the British unit and SI unit. In SI unit you just not use the GC term. In British unit you have to divide G to GC, and here also GC will come. That you have to remember. So you have to just substitute the value. Delta F is given, sigma F is given here. So once you substitute the value, it will come minus 60.678 LB fit LBF by LBM. So this is the unit of the energy. So the 60.678 is the requirement if the mechanical energy requirement for the system. Now you have to calculate the requirement of pump. So the efficiency pump is 65%. So you have to just divide this equation to the 65%. So 60.678 divided by the 0.65. So it will come 93.3 fit per LBF or LBM. Now you have to convert it in the horsepower. So for converting, this is the energy requirement of the pump in the British unit. Now you have to convert it in the horsepower. So for converting in the horsepower, first you have to calculate the mass flow rate. So just multiply the volumetric flow rate to the density, it will convert in the mass flow rate, and mass flow rate multiply by the multiply by the this energy requirement, multiply by the we converting, this is the ratio of the 1 horsepower to the lbf per second. Okay, this is per unit, this is the energy requirement per unit mass. So you have to calculate the power. When you have to calculate the power, that should be the energy requirement per unit time, that is the power of the pump. Horsepower is the power, so power is the energy per time, and this is the energy per mass. That's why you have to multiply with mass, and that then you have to convert this in the horsepower. It will come around the 3 horsepower. So you need the 3 horsepower pump for flowing the fluid in this system. So I am suggesting you to solve the same problem, both problems, and try to determine try to solve the understand the problem, then solve the problem. Now again they have the calculated the velocities at the different point, and the here you calculate the power requirement of the pump. Now at the point 3 and point 4, if you do the material balance at point 3 and point 4, you can calculate, because the here the uh, elevation of the system is same for point 3 and point 4. The potential energy will same, only the kinetic energy will different, or kinetic because energy will different because you have the different size of the pipes, and the pressure energy will different because you are giving this energy to the system. We are working on the system by using this pump. So here you can calculate the V3. V3 is calculated by volumetric flow rate will be same 0.1539 divided by the cross sectional area. You will get the V3. You can calculate the V4, that is the volumetric flow rate divided by the cross sectional area, that will be 6.61, or V4 equal to V2, that you can also understand because here you have the same cross sectional area between the pipe 4 and 2. So because fluid is incompressible, so there should not be any change of the velocity between pipe 4.4 and 2. So you will get the same velocity here, V2. Once you calculate the V2, then you can do the other balance. So if you write the pressure difference between P1 and P2, because V1 is 0, okay, so P1 is 1 atmosphere, alpha is 1. So if you do the mechanical energy balance between so if you do the material energy balance between and mechanical energy balance between point 3 and 4, so you can write this equation here. So you just calculating the pressure difference between point 3 and 4, that is equal to P3 Z3, this is the potential energy difference, Z3G divided minus Z4G, because both point has the same elevation. We assume that both point has the same elevation, that means the potential energy difference will be 0. Then you have the V3 square minus V4 square. You just calculated the V3 and V4 here, so you know the V3 and V4 here. So when you use the equation, you will get this terms as a V3, this term as a V4. Then the here in between point 3 and 4 you have the pump also, which is the point 3 and point 4. This is the point 3, this is the point 4. So in between point 3 and point 4 you have the pump also. So just substitute the power produced, which we have calculated right now, by the pump. Mechanical energy of the pump, that is the 60.678. This is the per unit mass minus delta sigma f. So sigma f is the friction losses, because here only the pump is present between the pipeline. So there we assume that there is a no friction loss between point 3 and 4. So when you assume that there is a no friction loss between point 3 and 4, you can assume that sigma f is 0. So when you substitute all the values, you can calculate the P3 minus P4 equal to 40.48 lbf divided by inch square. So the pond's pressure psi, this is also in the psi, this is also called the psi. So 48 psi, this is the pressure developed by the pump in the system. P3 minus P4 signifies that the how much pressure is developed created by the pump on the system. Now there are some more problem given here, simple problems when using the Bernoulli equation. So you can solve these two problems also. So basically in this problem we are calculating the flow rate of flow from pressure measurement. So suppose this is used when you are calculating the, this equation is basically used in this problem. Here you have the Bernoulli equation. So we are using the we are solving the some problem using the Bernoulli equation. Basically these are the derivation in the special cases. So suppose you have to calculate what is the value of V2 when you change the diameter of the pipe. So this happened when you use the in terms of pressure, so this equation is used when you are using the Venturi meter or the orifice meter. When you use the Venturi meter and orifice meter, then you change the, basically you change the diameter of the pipe and you calculate the velocity in terms of pressure. So we will develop that. So here you have a liquid with constant density rho is flowing in an unknown velocity V1. V1 is not known to you. What is the V1? Through a horizontal pipe of cross-sectional area A1. Here the cross-sectional area is A1 at a pressure P1. Pressure is P1 here. And then it passes to a section of the pipe in which the area is reduced to A2. So here you reduce the area to A2. The pressure becomes P2 and velocity is comes from V1 to V2. Now you have to just calculate the value of V2 in terms of pressure difference. Okay, so for that first we substitute the value of V1 in terms of pressure difference, suppose. So first we use the equation of continuity in the macroscopic balance. So V1 rho 1 A1 equal to V2 rho 2 A2. That is the equation of continuity or mass balance for the system. Okay, rho 1 A1 V1 equal to rho 2 A2 V2. Now rho 1 equal to rho 2, it is given here. Rho 1 equal to rho 2. So when rho 1 equal to rho 2, then you can write V2 is as a V1 A1 divided by A2. So this is the value of V2. Now because here there is no elevation change between 2 points, here we assume that this is the horizontal line. That's why we are using the orifice meter and Venturi meter in the horizontal pipe. We generally not use the Venturi meter and orifice meter in the vertical line. We just use that flow meters in the horizontal lines. So Z1 and Z2 are 0. So just write the Bernoulli equation. You will write Z1 G, that is 0, plus V1 square by 2 plus P1 by rho equal to Z2 G, that is 0, plus V2 rho divided by V2 square by 2. So V2 square equal to V1 square A1 square by A2 square by 2 plus P2 rho. So this is the same equation. Now you can calculate P1 minus P2 equal to this equation. Here V1 comes out, so you will get this equation. Now you can rearrange this equation 2.735. You can rearrange this equation. You will get V1 equal to under root of P1 minus P2 by rho multiplied by 2 divided by in bracket A1 by A2 square minus 1. So this is the value of V1. Similarly, you can calculate the V2. So V2 will equal to under root P1 minus P2 by rho multiplied by 2 divided by 1 minus A2 by A1 square. So this is the value of V2. So in this way you can use the Bernoulli equation to calculate the value of V1 or V2 in terms of pressure difference, which is used in the Venturi meter and the orifice meter. Now second example is rate of flow from a nozzle in a tank. So in this problem it is given that you have a large tank of water which is filled with a fluid like water, incompressible fluid. Now you have to calculate, there is a small outlet at the bottom of the tank and you have to calculate the velocity at the bottom of the tank. So here you have to solve this problem, that a nozzle of cross-sectional area A2 is discharging to the atmosphere and is located in the side of a large tank in which the open surface of the liquid in the tank is a meter above the center line of the nozzle. Calculate the velocity V2 in the nozzle and the volumetric flow rate of discharge if no friction loss are assumed. So here we assume that friction loss is 0 and there is a no pump there, so the work done by the surrounding on the system or work done by the system on the surrounding will be 0. Ws will be 0 and sigma f will be 0. So you can use the Bernoulli equation. Okay, here you have the pressure difference in these 2 points P1 and P3, and you have the pressure difference between P1 and P2. So here you have the higher pressure due to the weight of the system, weight of the water above it, but here you have the atmospheric pressure. At the point P2 you have the atmospheric pressure. The second point is the velocity V3 here is 0. Here velocity V1 you can assume it is also 0, but you have the velocity V2 here. Okay, so when you apply the Bernoulli equation between point 1 and 2, so one point is the inside the water at the same level of the inside the tank at the same level of the V point 2 where the opening is situated, and second point is the just outside the opening, so there the pressure is equal to the atmospheric pressure. So you are applying the Bernoulli equation between point 1 and point 2. So Z1g plus V1 square by 2 plus P1 minus P2 by rho equal to Z2g plus V2 square by 2. Okay, here Z1g equal to 0, Z1g minus Z2g equal to 0. Why? Because both have the same elevation. Z1g and Z2g have the same elevation. P1 minus P2 by rho equal to then V2 square by 2. Okay, V1 square by 2 is 0. Why V1 square by 2 is 0? Because this is a large tank, so the velocity at the inside the tank at the same level, inside V1 point is situated inside the tank, so at that point you can assume velocity is negligible enough. Why? Because the amount of fluid is so much large that the small amount removing from the point 2 will not affect the velocity of the molecules inside the tank. So V1 by 2 equal to 0, so you will end up P1 minus P2 by rho equal to V2 square by 2, which will leads to this result, V2 equal to under root of 2 P1 minus P2 by rho. Now you have to calculate now we will write the equation, Bernoulli equation between these 2 points 3 and 1. Why? Because in these 2 points the difference of mechanical energy is based due to only the potential energy. The kinetic energy will be same because velocity of fluid at V3 here is 0, velocity of fluid at V1 point is 1 point is 0, V1 is 0 because size of tank is large. The second the change is due to the pressure difference. So whatever the pressure difference comes from here to here, that is due to only the potential difference. Kinetic energy will be 0. So P1 minus P3 equal to jet rho g. Okay, so P1 by rho minus P3 by rho equal to Hg. So this is the Bernoulli equation. So when you write this equation, it will comes out that P1 minus P3 equal to H rho g. So this is the Bernoulli equation between the point 1 and 3. Now we can, if you check this diagram, this point 3 is at the atmospheric pressure and this point 2 is also at the atmospheric pressure. So the pressure of the at both point are the are same. Okay, so you can write P1 equal to P2 because this is also outside the open in the atmosphere, this is also outside open in the atmosphere, so the pressure at the point 3 and point 2 will be same. So here you can assume P1 equal to P3 equal to P2, and when you assume P3 equal to P2 in this equation, you can substitute you can replace P3 to the P2. So when you replace P3 to the P2, you will end up this equation H equal to P1 minus P2 rho g. Now from equation 2.741 and equation 2.740, here V2 equal to under root 2 P1 by P2 rho. So just substitute the value of P1 by P1 minus P2 rho in this equation from equation 2.741. So you will get the V2 equal to under root 2gh. So this is the value of V2, velocity based on the height of the fluid inside the tank. So by using this equation 2.742, you can calculate the velocity of fluid here by determining the height of the fluid inside the tank. Now you can calculate the flow rate, volumetric flow rate, that is equal to V2 multiplied by A2. When you calculate the V2 multiplied by A2, you can calculate the volumetric flow rate. Now if you write the now this is the again they write the same equation by using the point 2 and point 3. If you write the point 2 and point 3, you will get the same answer. Now this is all about the mechanical energy balance. Now in next class we will see that how to calculate the friction losses. So here in this problem friction losses are given, or we assume that friction loss are 0, but for a hydraulic system you have to calculate the friction losses inside that hydraulic system, then only you can calculate accurately correct the power requirement or energy requirement of the system. So in next class we will see how to calculate the friction losses in a system.